はい、それでは、始めます。環境触媒科学特論1の第5回です。はい。予定の変更はありません。No change in schedule. Today, I would like to talk about the adsorption. That is one of the most important phenomena included in photocatalysis, photocatalytic reactions. So, after the class, as usual, please send the email within 72 hours. So this is the sample, and almost all the attendees sent the email in this format. Yes. Last week, I explained the water splitting into hydrogen and oxygen by photocatalytic reaction. The principle is very, very simple. That is, the excited electron reduces proton or water into hydrogen, and at the same time, positive holes oxidize water into oxygen. So there is no remaining. Just water is decomposed into hydrogen and oxygen. So this is the reverse reaction of the usual spontaneously occurring reaction, that is the combustion of hydrogen to give water. And such a reverse reaction can be operated, can be make it possible by using the photocatalytic reaction. So why those studies have been initiated? Probably it started in 1970s. The important point is those studies of water splitting or energy conversion studies by using semiconducting materials have been initiated by this paper. This is the truth. This paper is written by Fujishima and Honda and published in Nature in 1972. And this is the whole paper, very, very short paper, only about 1 page in length. And probably now, up to now, this paper has been cited more than 17,000 times. 17,000回以上引用される。And one of the important points, some misreadings about this paper. The one is the order of authors. The first author is Fujishima, and the second author is Honda. And sometimes this is Honda and Fujishima's paper, but actually the order of names, authors' names, are Fujishima and Honda. And the other important point is this is very, very highly original paper. That is true. However, this is not the origin of photocatalysis by titanium in strict bibliographic sense. That is, this is just photoelectrochemistry, not photocatalysis. There are no words photocatalysis, photocatalytic or something in this paper. Just reporting the electrochemistry. The paper is electrochemical photolysis of water at a semiconductor. This is not a photocatalyst. And but this actually promoted the studies of photocatalysis. That is, because this shows the possibility of water splitting by solar light. That means by using the photoirradiation or photoreaction system, it is possible to the positive delta G reaction, that is energy storing reaction, can be available. That is the most important. So nobody knows such a positive delta G reaction can proceed by using photoirradiation. So therefore, it is very, very important. And this may solve the problem of energy. That is, solar energy can be converted into chemical energy. So therefore, this is the starting point. This is the truth. This is the starting point of such a study and showing the very, very important principle that is positive delta G reaction. Positive gives energy reaction change. And this is the important part. Please unmute the mics if you don't say something. If you have question or comment, please turn on your microphone. Okay. Just a second. Okay, then this paper is very, very strange because you see the figure 2 on the right side, and that is something like this. And there are the numbers 1, 2, 3, 4, 5. But there is no interpretation in this paper. Actually, no interpretation. So nobody knows what is 1, what is 2, and what is 3, 4, 5. And probably 5 is a voltmeter, and 4 might be resistance, and 3 might be the something dividing two cells of electro system. And probably 1 is titanium, and 2 is platinum, but then nobody knows. And therefore, many papers had been published after this paper to reproduce the results shown in this. And many papers claim that one should be titanium and 2 should be platinum and something. So the important point is in this paper, 2 examples of water splitting were reported. That is, one is the left side one, that is 2 electrodes, titanium and platinum electrodes are connected, but between them there is the electric source. So the voltage is applied, but this voltage is not enough to drive electrolysis of water into hydrogen and oxygen. And only hydrogen and oxygen evolution occurred under UV radiation. This is the bias potential application. On the right side, that is shown in figure 2. These 2 electrodes, titanium and platinum, are set in 2 chambers. One is the high pH for titanium electrode and the low pH for platinum electrode. Probably at the right side chamber, that must be the pH of 0. And for left side chamber for titanium, the pH is about 14. So the difference of pH between those 2 chambers are 14. And it is known that those difference of pH correspond to the potential. So 14 pH correspond to about 0.1 volt. So that is the same as the application of the bias voltage. So this is called the chemical bias. And the results, the reported results in this paper show that those bias potential application, electric bias or chemical bias, those bias application is necessary to drive this reaction. So that is important. Without those bias application, it is impossible to drive hydrogen and oxygen production. And the hidden message in this paper, not clearly told in this paper, but the hidden message of this paper is requirement of bias potential. The why bias potential is necessary. That is electric field inside the titanium electrode. Titanium electrode, that is the important. The electric field inside the titanium electrode is necessary to separate photoexcited electron and positive hole. That means that causes the charge separation. So without charge separation, due to electric field inside of the titanium electrode, it is impossible to drive hydrogen and oxygen production. So the hidden condition, not clearly shown, described condition for water splitting is positive Gibbs energy change reaction. That is the electric field inside the titanium is necessary. So this is a very, very important message. And actually, it is impossible to apply bias potential in photocatalytic reaction system using particles. So in that case, it is impossible to apply the electric field to make electric field inside particle. So therefore, it is a bit different from the electrode system. So in this sense, this paper, Fujishima and Honda's paper in Nature, cannot be origin of photocatalysis. That is completely different system of water splitting. However, the paper tells such a reaction can be driven if this scheme, the conduction band electron, can reduce something, and the positive hole in valence band can oxidize something. So by using this scheme, it is possible to drive many types of reactions under photoirradiation of semiconductor photocatalysis. And the important point is this is just a thermodynamic aspect and not including kinetic aspect. So actually, for as I told you, the paper in Nature tells the actual current flow, that is hydrogen and oxygen evolution, requires the electric field inside of the titanium. That means that is a kinetic, so not a thermodynamic. Thermodynamically possible, but without application, it is impossible to drive the actual reaction. That is kinetics. So then, last week, I introduced the thermodynamics and kinetics. And actually, this is just probably you already know that is the thermodynamics is equilibrium. So the thermodynamics is controlled by Gibbs energy chain. And for the reaction shown in this picture, the source is converted into product. In that case, the thermodynamics tells the difference of energy between two states. One is source, one is product. And the difference of Gibbs energy is important to predict how those reactions proceed. And in this case, the energy of source is higher than that of product. Therefore, the reaction proceeds into the right-hand side. So the source is converted into product. This is thermodynamics. And then the kinetics. The kinetics is just the velocity of reaction to reach the equilibrium. And as the thermodynamics tells, the source is converted into product. And what is the meaning of this? That is, we need to think about the activation energy. And there are two kinds of activation energy. From source side, the EA is smaller than EA, activation energy from product. And the higher the activation energy, the slower the reaction. And that means the difference of EA and EA prime, that is the delta G, gives the difference in the rate. And actually, the rate of right-hand side reaction from source to product is higher. The rate is higher than the rate of backside reaction. So actually, the product can be obtained from source. Okay, so this is the general understanding of thermodynamics and kinetics. And then we need to think about photocatalysis. And what is the meaning of activation energy in kinetics of photocatalysis? And then the activation energy of ordinary chemical reaction, that is a few hundred kilojoule per mole. So the wide variety of those, the energy, but in average, the ordinary chemical reaction has the activation energy of few hundred kilojoule per mole. And that can be reduced by catalysis, not photocatalysis. In the ordinary thermal catalysis, the catalyst reduce this activation energy to small. Therefore, the reaction proceeds smoothly. And this is not so recent papers, but many papers have reported the activation energy of photocatalytic reaction by the changing the temperature of reaction. And here, only the example of those reported activation energies are shown. And almost all the activation energy of photocatalytic reaction is very small. The highest one is about 25 kilojoule per mole. That is still very low compared with the catalytic reaction. And the smaller one is about 4.2 or something. So very low. So that means in photocatalytic reactions, there are no activation energy. So what does it mean? So that means it is impossible to say something about the kinetics, that how fast reaction proceed. For the rate of reaction, it is impossible to predict the rate using activation energy for photocatalytic reactions. So this is completely different from the ordinary thermal catalytic reactions. So therefore, the activation energy cannot be the tool for predict the kinetics of photocatalytic reaction. So for those how the rate of photocatalytic reactions are expressed, probably the next week and the next week I will interpret you how to predict the kinetics of photocatalytic reaction. And for making those discussions, before discussing this reaction rate, we need to think about the sorption. So the phenomena of photocatalytic reaction, that is the photoirradiation to titanium or the other metal oxide particles, led to some chemical reaction. Had been already known in 19th century, but at that time no term of photocatalysis or photocatalytic reaction. So therefore, they don't understand this. But actually, they observe the phenomenon of change of something under photoirradiation. So that is the one example is choking. Choking is maybe you know the chalk on blackboard. That is the paint coating is degraded to be white powder. That is under exposure of sunlight, the paint coating contains titanium as a pigment, and the titanium drives photocatalytic reaction to decompose binder. Binder is the organic compound that binding those pigment, and therefore it is possible to paint on the surfaces. And titanium decompose those organic compounds to carbon dioxide. So therefore, the titanium particles are exposed on the surface. Therefore, that is something like a chalk. The white powder appeared under photoirradiation. So this is chalking, and that means the binder was in contact with titanium particle. So therefore, only the compound in contact with titanium can be decomposed. So that is the important. And I introduce you some application of photocatalysis. And one example is this air purification. In air conditioner or in air purifier, the titanium photocatalytic devices are included. And in that case, the air, the indoor air is introduced into this device, and the compound included in those air is in contact with the surface of titanium photocatalyst. So therefore, again, only the compound in contact with titanium photocatalyst can be decomposed. So therefore, only by putting those devices in room doesn't work. So it is necessary to introduce indoor air into this device. This is the important again. And the other application of titanium photocatalyst is photorod. That is the surface pavement include the photocatalyst titanium. To the purpose of this coating is to decompose nitrogen oxide NOx to be NO3 minus, and that can be removed by calcium nitrate to the running rainwater. So that is important. So that is a very, very good device. However, only the nitrogen oxide coming to the surface of titanium or catalyst can be decomposed. And almost all those NOx in exhaust gases of automobiles cannot reach to the surface of titanium for the catalyst that is expanded. So, and no contact with titanium. So therefore, it is impossible to remove all the nitrogen oxide from automobiles can be decomposed. Not all, only the part. So therefore, the only adsorbed compounds can be reacted. That means photoexcited electron and positive holes, they cannot go out. So just on the surface. So only the surface adsorbed compound can react with electron and positive hole. So therefore the adsorption is very, very important. In Japanese, 吸着。吸着されたものだけが反応します。ここはとても重要な。電子や星光は外には出ません。表面に吸着された物質だけが反応できるということです。吸着は日本語ではどちらもある。吸着する、吸着されるどちらもあるんですけど、英語はいつでも、パッシブになります。So, then we need to think about adsorption isotherm. Isotherm is, iso means equal. The therm is temperature. So the isotherm means the something measured at the constant, the same temperature. And how the compound is adsorbed on the surface. The term is very, very important. In Japanese, 吸着質 that is adsorbate, that is compound. Adsorbate is adsorbed by adsorbate. Adsorbent is in Japanese 吸着剤。吸着剤が吸着質を吸着する。主語は吸着剤。吸着するという動詞は吸着剤が吸着する。吸着質は吸着される。adsorbent, adsorbs, adsorbate. Adsorbate is adsorbed by adsorbent. And the interaction between adsorbate and adsorbent, if that is van der Waals force, that is called physical adsorption. If some chemical bond is created between adsorbent and adsorbate, that is chemisorption. In my student days, chemisorption is chemisorption, not chemical adsorption. And physical adsorption is just a physical adsorption, not physisorption. There was no term physisorption in those days about 40 years ago. But now it is possible to say that physical adsorption can be called physisorption again. So anyway, the adsorption is categorized into two. One is physical adsorption by van der Waals force, and the other one is the chemical adsorption, chemisorption with chemical bond. But actually, intrinsically, no difference between them. Just the adsorbent adsorbs adsorbate. And probably you can imagine that if the concentration of adsorbate is high, the amount of adsorbed adsorbate must be high. And if the adsorbent has high ability to adsorb something, the amount of adsorbate adsorbed on the surface is high. So we need to think how much amount of adsorbate is adsorbed on the surface under the the given conditions. So to measure this dependence, that is the dependence of adsorbed amount with concentration or pressure of adsorbate is called isotherm. So that means the x-axis is equilibrium pressure or equilibrium concentration. And here, the four panels, four plots, that is the x-axis, the same, the pressure or concentration. If the pressure or concentration of adsorbate is changed, how the amount of adsorption is changed. And there are at least four types of those isotherms, dependence of adsorption on concentration or pressure of adsorbate. So those typical four isotherms, they are named. Please answer. What is A? A is called something, B is, and C and D. And all these names of isotherm is name of scientist. So answer, please. 言いましたか？まだ書いてない人、わかんなくても何か書いてください。誰かの名前です。いいですか？大丈夫？はい。こういうことになってます。直線的に増える。The linear plot is called Henry. And this type to be saturated, 飽和する形のもの。This is called Langmuir. And this stepwise one is Brunauer Emmett-Taylor. This is, in general, this is called BET. And sometimes this is called BET. No. This is the three names, B, E, T, Brunauer Emmett-Taylor. So therefore, this should be told BET, not BET, BET. And the gradually increasing one is called Freundlich. In German, that is Freundlich. And actually, many Japanese scientists call this Freundlich. But in English, this is Freundlich. So anyway, except for Henry, the other three isoforms are reported by those scientists, chemists. And probably Henry is not discovered by Henry. Henry is the scientist who discovered the dissolution of gases in liquid. So the solution, the solubility of gases, Henry reported the solubility, the amount of this solved, the concentration of the gases in solution is linearly increased with the pressure. That is the Henry's law for gas dissolution. And the type of plot is similar to that. So therefore, this is called Henry type. I don't think that Henry discovered this type of isotherm for adsorption. So anyway, one of the important points is the Langmuir adsorption isotherm can reproduce all the others. So in Langmuir adsorption, in the first linear part can be Henry, and if the several type of Langmuir adsorption is included in one adsorption phenomenon, that can be Freundly. And BET is based on the Langmuir adsorption, but that is multiple layer adsorption. So therefore, the essential isotherm for BET is Langmuir. So that is the multiple layer adsorption, Langmuir adsorption. So therefore, the Langmuir adsorption is very important. So it is possible to derive the Langmuir adsorption isotherm by using the very, very simple assumptions. Only by assuming 3 points, three assumptions, it is possible to derive Langmuir equation. So probably part of you have learned this Langmuir adsorption in undergraduate course. So please answer 3 assumptions for Langmuir isotherm derivatization, please. And if you don't know these assumptions, please imagine what kind of assumption is necessary. The important point, the basic concept of adsorption is there are the site for adsorption. That is just imaginary. So not the real. No need to the really there is such a the point for adsorption, but that is it is possible to assume there are sites for adsorption, and those sites can adsorb something. So this is the starting point. And based on this assumption, the Langmuir assumed 3 points for making Langmuir isotherm. So please answer. So those three assumptions are related to this the site for adsorption. The conditions of those sites, how those sites works, and what are those adsorption sites. And in this picture, O means occupied, and the V means vacant.はい。はい。これが3つの過程です。all are related to adsorption sites. First, all the adsorption sites are same in quality. So that means strength of capturing adsorbate is constant. 吸着サイトは均一である。どのサイトも同じ力で、吸着できる。どこが強くてどこが弱いとかそういうのはなくて、全部同じですというのが、一番の過程です。これがないとなかなか、定式化するのは難しいです。The second, only one adsorbate is adsorbed by one site. Once the site is occupied by adsorbate, it is impossible to further to adsorb further. 1個のサイトには1個の吸着質しか吸着されない。1個埋まってしまうと、次はもう来ない、というのが、まあ、当然といえば当然の過程になります。The third, there is no interaction between sites. That is, adsorption not influenced by adsorption of neighboring sites. 吸着サイト間の相互作用はない。吸着サイト間の相互作用というか、一旦吸着されたら、それが周りに影響を与えない。隣が吸着されているか、吸着しているか、吸着していないか、隣のサイトが吸着しているのかしてないのかということは関係ありませんというわけです。それぞれ独立。だからこう、隣が吸着しているのでちょっと邪魔になって、入りにくい。そういうことはないということです。So there are no interaction between them. So then, only by using those assumptions, that is very, very simple. That is natural, almost natural assumptions. And by assuming those 3 points, it is possible to derive the Langmuir equation. And then it is necessary to remind that the adsorption, we assume, we think the adsorption equilibrium. Probably you know that what is the meaning of equilibrium. Equilibrium is same rates of forward and reverse reactions. So forward reaction is adsorption, and the backward reaction is desorption. 日本語だと吸着アドソープションと脱着と言います。デソープション。ここで考えるのは平行ですから、吸着平行を考えますから、吸着する速度と脱着する速度が等しい。これがエクイリブリアムです。So, and then, how those rates of adsorption and desorption are controlled. For adsorption rate depends on two points. One is concentration in the bulk of adsorbate, and two, the number or density of vacant site. So if all the adsorption site is occupied, it is impossible to adsorb. So therefore, the two concentration or density determines the adsorption rate. On the other hand, desorption rate depends only on number or density of occupied sites. So desorption rate doesn't depend on the concentration of adsorbate inbound. 吸着は吸着されるものの濃度、あるいは圧力に依存します。当然。で、もちろん空いてるのがどれだけかということにも依存します。空いてなければ吸着できません。で、だから2つに依存します。しかし、脱着の速度は、外にどれだけあるか全然関係ないです。外にいるから脱着しにくくなるわけじゃなくて、脱着する速度は、occupied site、吸着しているサイトのデンシティだけで決まります。これがたくさんあったら脱着の速度は速いだけで、外にたくさんあろうとなかろうと、脱着の速度そのものは、脱着だけを考えたら、外の濃度は関係ありません。これがデソープション。いいですか？ここすごく大事です。この2つの速度、アドソープションレイト、デソープションレイト。この2つで平行が決まるわけです。この2つが等しい。で、じゃあ、速度ってどうですか？もう一遍戻ります。これはすごく、基本的なところ。So this is just a general explanation of reaction kinetics. And assuming the reaction A to B. So this is not equilibrium. That is that reaction, one reaction from A to B. And in that case, we assume the rate constant K, small k. So how the rate of R is expressed by using the rate constant and the concentration of A and B. Please write. R equal what? すごく基本的なところです。反応間です。これ平行じゃない。反応間が A から B という反応間。この時にレートコンスタント。反応速度定数 K。小文字の K。だとすると、反応速度。A から B へ行く反応速度。R というのは、この K と、A と B の濃度を使うと何と表されます。すごく簡単な問題です。So, is it okay? はい。F is forward reaction. From A to B. And RF equal KF concentration A. So there is no dependence on concentration B because only A is converted into B. So this is forward reaction. So when we assume the backward reaction, that is RB backward equal KB B. So this is, and when we assume the equilibrium in those two forward and backward reaction, at the equilibrium, the RF equal RB. So then, in that case, KF over KB, that is called equilibrium constant, large K, equal B over A. This is equilibrium. Okay? Is it right? And this is general chemical reaction. And then this type of discussion is used in adsorption equilibrium. RF is adsorption rate, and RP is desorption rate. So again, adsorption rate depends on concentration in bulk and number of vacant sites, V. And the desorption rate depends only on number of occupied sites. Okay, so then the theta equal Kc over 1 plus Kc. This is the Langmuir adsorption, isosum. So this is the goal. And the starting point is rate of adsorption, Ra, and rate of desorption, Rd. And the concentration or density of vacant site is shown V, and occupied sites O, and the coverage theta equal O over V plus O. And the concentration at equilibrium, that is C. And the rate constant, Ka, Kd, that is for adsorption and desorption. And the adsorption equilibrium constant, large K, equal Ka over Q. Okay, start from showing the rate of adsorption Ra and Rd, and then that is changed, derived into the final Langmuir adsorption isosum, theta equal Kc over 1 plus Kc. Please. Langmuir isosum、Langmuir吸着等温式では、平行感です。平行というのは、アドソープション、吸着する速度と脱着する速度。これが等しいということになります。で、ここで使うのは、ベーカントサイト V、空いてるサイト V と吸着しているサイト O で、被覆率、カバレージ、シータは被覆率と日本語では言います。これは、O を V プラス O で割った。つまり全体のサイトの数のうちで吸着しているところの割合。それがシータ。で、コンセントレーション。これは当然、最初は違うかもしれないけど、吸着平行に達したときに濃度が C。これ外側の濃度です。全体の、基質の量じゃなくて、外側の吸着されていないものの濃度です。で、レートコンスタントがスモール k とスモール k。これは吸着速度と脱着速度式に出てくる速度定数。で、adsorption equilibrium constant、平行定数。吸着平行定数、ラージ K というのは Ka を Kt で割ったものです。で、したがって、RA と RD、スモール RA とスモール RD をこれらのパラメータで表して、最終的に一番下にあるシータが Kc を1プラス Kc で割ったものになるように、出てくる V とか O とか Ka、Kd 全部消さない。消せばこれになります。この式を誘導してください。どうぞ。 このラングミアの吸着等温式を導くっていうのは、まず速度論の基本が分かっているか、それから平行、熱力が分かっているかという、二つのこと。両方とも必要というか、それがちゃんと分かっているかっていうことを確認するのにすごくいいものになっています。はい。書けました？またできてませんっていう人いますか？大丈夫ですか？はい。簡単に言えばこうなります。先ほど言ったように、吸着の速度は空いてるサイトと外側のノードで決まります。で、脱着の方は、吸着している、つまり占有されているサイトの密度だけで決まります。外側のノード関係ありません。で、それぞれに速度定数が入ります。The rate of adsorption is shown like this, and the rate of desorption is shown like this. And the important point is for rate of desorption, no C is included. And for equilibrium, those forward and backward reaction, the rates are same. So therefore, KAVC equal KDO. And starting from this, so it is necessary to cancel out. So to make those small k and small d, v and o should be deleted. So to delete k and kd, it is one possible way is both sides is divided by kd. And also v is and both sides is divided by v plus 4. So actually, by using this, the derivation is made like this, and then at last we obtain theta equal kc over 1 plus kc. No k a the rate constant ka, kd, and v and o are included. And Ka and Kd is changed to equilibrium constant, large K. And V and O is removed by using theta. Okay, so this is the derivation. So every time such a derivation is very important for kinetics and also thermodynamics. So I strongly recommend to learn how to derive Langmuir isosan equation. That is very important, and please check it again and again. And this is the results of our from our laboratory. The rate of silver metal deposition, that is, the silver metal is deposited on the surface of titanium under photoirradiation. And the rate of this silver metal deposition is plotted against as a function of amount of silver ion, that is the starting material. Silver ion is reduced to silver metal. And the amount of silver metal is the dependence of rate on the amount of silver ion is plotted like this, and almost linear relation is obtained. Here, the small numbers, figures, the highest one, the 8.05, that is the pH of reaction. And by changing the pH of solution, the amount of silver ion is changed, was changed. But the total overall reaction rate depends only on the amount of silver ion on the surface, not to depend on the concentration of solution. If the amount of adsorbed silver ion is the same, the different concentration silver ion solution gave the almost the same reaction rate. So this is very important. So therefore, it is possible to predict the reaction rate by assuming the adsorbed amount of substrate. So this is very important. Okay, and then one of the important points of this Langmuir ice that is very important point is the actual amount of substrate adsorbed on the surface is shown like this. S others. This is the amount of or density of substrate adsorbed on the surface. That is theta. Theta is just the ratio. How much proportion of adsorption site is occupied by adsorbate. So therefore, a small s is introduced. Small s is the saturation amount of s. That is, if all the adsorption sites accept adsorb substrate or adsorbate, that is s. So s is the total density or amount of adsorption site. So therefore, S multiplied by theta, this theta is the actual amount of adsorption. So that, and then the theta equal Kc over 1 plus Kc. So therefore, this S theta equals to SKc over 1 plus Kc. 実際の吸着量はこのように表されます。シータというのは割合を表しています。空いているサイトと、吸着しているサイト、つまり全部のサイトに対して、吸着しているサイトの割合をシータで表します。なので、全体の吸着量、ごめんなさい、吸着できるサイトの密度、あるいはその数、あるいは量を S で表すと、S シータというのは実際に吸着されている量ということになります。で、シータが Kc オーバー1プラス Kc ですから、それに S をかける、スモール S をかけると、SKc オーバー1プラス Kc というのが実際の吸着量ということになります。で、これが基本の式です。ランドメア式の基本の式。で、これに対して、2つの、リミットを考えることができます。There are two possible limits. One is the C concentration of adsorbate in solution is very, very low, very, very small. In that case, the Kc can be neglected. That is very, very small. So in that case, the S others is proportional to something. And the another limit, that is, the other limit is when Kc is very, very large. So in that case, the 1 in 1 plus Kc can be neglected because Kc is very, very large. So in that case, how much is the total adsorption? S others. Please fill up this. はい。こうなります。C が小さければ、1プラス KC のうちの KC の部分がなくなっちゃうので、吸着量は SKC になります。でそうすると、吸着量は濃度に比例する。非常に濃度が薄い領域だと濃度に比例します。So when the C is very small, the Kc in K1 plus Kc is neglected. So therefore, the S adds equals to SKC. So therefore, the amount of adsorption is proportional to the concentration C. And if C is very large, in that case, 1 in 1 plus Kc is neglected. So therefore, Kc disappeared. So therefore, the adsorption is become the same as S. Of course, all the adsorption site is occupied, and no further increase. So if all the adsorption site is occupied, so no further increase in adsorption happens. So therefore, this is the limitation. Of course, this is the limitation. C が小さければ1プラス KC のうちの KC はなくなるので、吸着量は SKC で C に比例する。もし、C が大きければ1プラス KC のうちの1が、無視できるので、そうすると KC を KC で割ってしまいますから、S アドスは、スモール S になる。まあ、当然です。全部の吸着サイトが非常に濃度が高くなっていたら全部吸着されてしまって、まあ、それ以上増えることはありませんから、そこで止まってしまうというわけです。So, therefore, in the lower concentration range, that is almost linear. That is almost proportional to the concentration. So this is Henry type absorption. So if the concentration is very small for Langmuir isothermal adsorption, that is similar to the Henry type adsorption. And if the concentration becomes very large, in that case, the amount of adsorption is approaching to the limit S. So this is the highest limit. So the adsorption amount is approaching to the limit S. And the very, very high concentration range, that is almost equal to S. So it is possible to find out how much amount of adsorption sites are there on the surface of the adsorbent. So it is possible to see those limits. Okay, so this is a very, very simple Langmuir adsorption problem. And then, so you should remind those derivation. So this type of derivation is not limited to Langmuir isotherm derivation. That is very important point. And you should remind those processes making those derivations. And the other important point is this essential assumptions for derivation of Langmuir isotherm. All the adsorption sites are same in quality. That is, the strength of capturing the adsorbate is constant. And only one adsorbate is adsorbed by one site. Yes. And there is no interaction between sites. That is, adsorption not influenced by adsorption of neighboring sites. So probably this is not so strange, but actually very, very strange point is this Langmuir adsorption isotherm based on this three assumptions. That is, there is no concept of surface is included in this Langmuir isocycle. So the first one, all the adsorption sites are same in quality. And the one adsorbate is adsorbed one side. And no interaction between sides. That means you can assume adsorption site is something like a molecule. So in that case, such adsorption site is assumed to be molecule. If the same molecule is used, the adsorption, that is the reaction with adsorbate, the reaction ability is the same, of course. Same compound, same molecule can react with the other molecule in the same way. And one molecule, the one absorption site molecule, can react with one adsorbate, of course. And there is no interaction. If one adsorption site molecule is reacted with the other adsorbate, there is no interaction with the other adsorption site molecule. So that means these assumptions say the adsorption site is something like a molecule. So no concept, no influence of surface. The adsorption site must be on the surface. However, there is no limitation of that. Even if the adsorption site is something like a molecule dissolved in water or solvent, that can obey, that can follow the adsorption isocycle. この3つの過程というのは、そんなにおかしくないように見えるんですけど、よくよく考えてみると、この3つの過程というのは、全く表面ということを考えてません。吸着サイトというのが一つの分子だとする。その分子が吸着質である別の分子と反応すると考えます。その分子が同じ分子なら当然反応性は一緒だから、一番最初の過程は当然成り立つ。で、一つの分子は、吸着質という分子と1回しか反応できませんので、1個はくっついてしまったらもうそれでおしまいですから、2番目の one adsorbate is adsorbed by one site っていうのは、1個の吸着サイト分子が吸着質と反応したら、それで終わりっていう意味です。で、吸着サイト同士のインタラクション、相互作用がない。それは当然で、普通の反応の時に、別のやつが反応したから僕は反応しないっていうようなことはないので、全くそこは独立に反応します。だから、この3つの過程というのは、吸着サイトという分子が均一な溶液中とか、ガス中にあるのと一緒です。表面にそういう吸着サイトが並んでますと。そういう効果を全く考えてないわけです。なので、また来週やるかもしれないですけど、ミカエルスメンテンの酵素の反応速度、の式なんですけど、反応速度の式ってあるんですけど、これはラングミアの吸着等温式と非常に似てます。それは当然で、酵素っていうのが一種の吸着サイトとして考えれば同じことが起こっているわけです。したがって、ラングミアの吸着等温式は非常に多くの現象を説明可能です。可能だけど、実は表面ということは全く考えていません。ここはすごく大事なことです。先ほど説明したように、ヘンリー式というのはラングミア式の濃度が薄いところと思えばいいです。フロインドリッヒ式っていうやつは、 これは複数のサイト、複数の吸着力のあるサイトがあって、それぞれがラングミア型でそれを足し算したという形です。ブルナー・エメット・テラーというのは、一番濃度の低いところの最初の部分はラングミア式なんです。だけど、ラングミアの過程では、1個のサイトには1個しか吸着しませんって言ったんですけど、ブルナー・エメット・テラーの式では、1個吸着した上にさらに吸着できるという過程を入れています。でも2段目も、基本的にはラングミア式。1層吸着した上に2層目が乗るという部分もあるだけで、基本的にはラングミア式。ラングミア式を拡張しています。だから、どの式も、普通に考えられるどの式も、4つとも、もともとはラングミア式として考えてよろしい。これをただ変形した、あるいは別の過程を少し入れただけです。だけど、もともとのラングミア式っていうのは、表面の効果を考えているのかというと、実は全く考えていない。これが不思議なところです。吸着というのは、それほど難しい話ではなくて、実は普通の溶液中の分子と分子の反応と同じようなものなんですけど、でも、実際の吸着現象は説明できてしまう。だから我々が思っている表面の効果っていうのはそれほどない。But again, those representative for reaction adsorption isoforms can be derived from Langmuir isoform. The Henry type adsorption isoform is the part of Langmuir isoform at very low concentration range. And Freundlich isoform can be reproduced by overlapping the several Langmuir isoforms. So different adsorption sites are there. And Brunauer method that assume the multiple layer adsorption. The first layer in the left side, those part is the same as Langmuir adsorption. And the second one is the adsorption of second molecule, second adsorbate on the first layer. This mode is almost the same as the Langmuir, just a bit complicated Langmuir adsorption. So therefore, those four representative adsorption isoforms can be derived from Langmuir adsorption isoform. But the basic Langmuir adsorption equilibrium isoform is not considering the special effect of surface. The adsorption site works independently like molecule. So that is a very important point. We think those surface phenomena is a bit complicated, and that is a bit different from the ordinary reaction in solution or gas phase, the homogeneous system. But actually, Langmuir clearly tells that that is not so complicated. That is almost the same as the homogeneous reaction. Only the sites are there on the surface. There is no special effect of the surface. That is important point of Langmuir isoform. And I will, if I have time, we have time, I will interpret you again for this, the very important, significant point of Langmuir isoform. So then, today's lecture is over, and please remember again those derivations of Langmuir isoform. And okay, so then today's lecture is over, and please send email in Japanese or English within 72 hours. And the format is something like this. And today, June 4, therefore, the code name of this lecture is PC20200604, and your student number is necessary. And you should write the answer of all the questions. And you need not to correct or modify your answer after my talk. The answer should be what you think, what you make. You made. No need to correction. はい。それでは今日の講義はこれで終わりにします。はい。それではまた来週お願いします。